So what is a reversible reaction? Okay, in most of the cases that we considered in our previous class, we assumed that once the product is formed, it does not have the tendency to react and give back the original reactants. Okay, so such reactions are straightforward reactions taking place only in one direction, that is forward direction. But in some cases, the product formed, okay, have the tendency or chemical potential to react with each other and form the original reactants or give back the original reactants again. So such type of reactions are called as reversible reactions or opposing reaction. So suppose if I write this reaction A plus B giving C plus D. Okay, so the reactants A and B react with each other to form product C and D. However, the product C and D that are formed in this particular reaction have that tendency or chemical potential to react with each other and give back the original reactants A and B. So such type of reaction which proceeds both in forward as well as backward directions are called as reversible reaction. So a reversible reaction is represented by a half-headed arrow, okay, pointed in both the direction, forward direction as well as the backward direction. Okay, so the overall rate of this reaction will be decided by the rate of the forward reaction as well as the backward reaction. So the net rate of this reaction depends on the rate of forward reaction as well as the rate of backward reaction. How you can classify a reversible reaction? So a reversible reaction is classified based on the complexity of this reversible reaction. The simplest reversible reaction you can have is this reaction. Okay, A giving product and B in turn, okay, can give back the original reactant A. So this is the simplest reversible reaction where a first order forward reaction is opposed by a first ordered reversible reaction. So here the order of the forward reaction as well as the backward reaction is first order. So this is the simplest reversible reaction. Or you can have a reaction of the type A plus B giving C, okay, where the forward reaction is second order and the reverse reaction, backward reaction, is a first order reaction. So a second ordered forward reaction is opposed by a first ordered backward reaction. Okay, or you can have reactions of the type A plus B giving C plus D. Okay, so in this case both the forward as well as backward reactions are of second order. So a second order forward reaction is opposed by a second order backward reaction. So in this particular type of reaction, that is reversible reaction, there are two steps involved in the reaction. One is the forward step where the reactant is converted to product. The second step is the reversible or the backward step where the product is again converted or converted to the reactants. So when we are analyzing the kinetics data of such reversible reactions, we have to understand the or interpret the kinetic data of forward reaction as well as backward reaction. So generally what we do is we express the rate constant of the forward reaction as K1, where 1 represents the first step, which is the forward step, and we represent the rate constant of the reversible reaction or the backward reaction as K minus 1, where minus 1 reminds us that it is a reversible step. K1 is the forward step, minus 1 is the backward step. And some cases instead of K minus 1 we may even write K2 as the rate constant of the backward step. So in the analysis of a reversible reaction, we have to take into account the kinetics of both the steps involved in the reaction, that is the forward step as well as the reversible step. Okay, so if I give an example for a reversible reaction, you can have different examples. Okay, the one example for a reversible reaction is muta rotation of, okay, alpha D glucose into beta D glucose. So this is an example for a reversible reaction where alpha D glucose may be converted to the beta form, the beta D glucose, and this beta D glucose again has the tendency to reverse back and form alpha D glucose again. So you can express the rate constant of the forward reaction as K1 and the rate constant of the backward reaction as K minus 1. The other example for a reversible reaction is, okay, the another example that we can give for a reversible reaction is the conversion of NH4CNO ammonium cyanate, okay, into urea. Okay, interconversion of ammonium cyanate into urea. So this is also a reversible reaction. The rate constants are expressed as K1 and K minus 1 for the forward and backward reactions. So these are some of the examples for reversible reaction. As I told you earlier, when we are analyzing the kinetic data of such reversible reaction, we have to take into account the kinetics of both the forward as well as backward reaction. So now let us consider a very general and very simple reversible reaction. What do you mean by a simple reversible reaction? This is the example for the simplest reversible reaction, where both the forward as well as the backward reactions are of first order. So let us take this very simple reversible reaction and try to understand the kinetic analysis of a reversible reaction. So let us consider this reversible reaction, a very simple reversible reaction where a first order forward reaction is opposed by a first order reversible reaction A interconverted into B. K1 is the rate constant of the forward reaction, K2 is the rate constant of backward reaction. And in such type of reactions we can have two type of cases. The first case that we will be discussing is what happens if the initial concentration of product is 0. So the concentration of product B is 0 when time t is equal to 0. Let us try to figure out what is the kinetic analysis of this particular reaction. So let us first write the scheme for this particular reaction. So at t is equal to 0, that is reaction has not yet started, let A be the concentration of the reactant. So A represents, A moles per dm cube represents the initial concentration of reactant A. And what is the initial concentration of the product? Okay, the initial concentration of the product is 0 because the reaction has not yet started and I have not intentionally added the compound B to the container. Okay, because I might have already have prepared compound B on some other day and I may intentionally add it to the reaction mixture. Okay, I have not done anything like that. So reaction has not started, nor I have intentionally added compound B at the very beginning. So the concentration of B at t is equal to 0 is 0. At t is equal to 0 is 0. So what will happen is after a certain amount of time t, okay, after certain amount of time t, out of A moles per dm cube, x moles per dm cube of the reactant has reacted. And how much product is formed? Okay, the concentration of the product that is obtained after time t is also x moles per dm cube. So x moles per dm cube of A after time t has been converted to x moles per dm cube of product. Okay, so what is the overall or the net concentration at a time t? So let us calculate what is the net concentration at time t. So the concentration of the reactant A at a time t will be A minus x. Okay, because A is the initial concentration out of which x has reacted, so the remaining concentration is A minus x. And what is the concentration of the product at a time t? The concentration of the product at a time t is equal to x. Okay, concentration of the product at time t is equal to x. As I already told you, okay, as I already told you, when we are analyzing the kinetics of a reversible reaction, we have to analyze the kinetics of both forward as well as backward reaction, and the net rate of the reaction depends on the rate of the forward reaction as well as the rate of the backward reaction. So let us try to calculate the rate of the forward reaction and the rate of the backward reaction. So what is the rate of the forward reaction? Rate of forward reaction, okay, if I write it as RF, rate of the forward reaction, okay, is rate of the forward reaction, okay, is dx by dt. Rate is equal to, how do you write the rate equation or the rate law? Rate of a reaction is equal to rate constant into concentration of the reactant at the time t. So for the forward reaction, rate of the forward reaction is equal to rate constant for the forward reaction, that is k1, into concentration of the reactant. What is the reactant for the forward reaction? A is the reactant, so the concentration of the reactant A at time t. So rate of the forward reaction is k1 into A at time t, which is nothing but k1 into A minus x. So this is the rate of the forward reaction. Okay, let me take it as equation 1. Now let us calculate what is the rate of the forward reaction, so backward reaction. So rate of backward reaction, okay, if I write it as RB, R backwards, again rate is expressed as rate constant into concentration of the reactant. What is the rate constant for the backward reaction? It is K2 into concentration of the reactant at a time t. Since it is, now we are discussing about the backward reaction, B is the reactant for the backward reaction, so it is concentration of B at a time t, that is nothing but K2 into x. So equation 1 and 2 gives us the rate of forward reaction and rate of backward reaction. Now let us calculate what is the net rate of reaction. Or that is nothing but net rate of formation of product. Net rate of formation of product is equal to what? Okay, what is the net rate of formation of product? That is nothing but dx by dt. The net rate of formation of product is dx by dt. Okay, let us try to understand this situation by taking one example. Suppose I have initially 1000 molecules of A, okay, and at a particular instant of time, say for example 10th minute, 100 molecules of A has reacted. So what does it mean? How many molecules of B should be formed? At the 10th minute, 100 molecules of B should be formed at the 10th minute, okay. But what I observe is at the 10th minute there are only 60 molecules of B in the reaction vessel. There are only 60 molecules of B in the reaction vessel. So remaining 40 molecules of B LUO2, where did that 40 molecules of B disappear? Remember, this is not a forward reaction, okay. This reaction takes place in the backward reaction also. Even though at 10th minute there should have been 100 molecules of B, but out of 100, 40 molecules of B has reacted and has been again converted to reactant A. So one very straightforward reaction ಆಗಿದ್ದಿದ್ರೆ at time 10 t is equal to 10 minutes, there should have been 100 molecules of B, but there are only 60 molecules of B because 40 molecules of B has been reconverted to A. So expected was 100, but how much is left? There is only 100 minus 40 because 40 has been reconverted, so there is only 100 minus 40, that is 60 molecules of B. So for a reversible reaction, the net rate of the reaction ತಗೊಳ್ಬೇಕಾದ್ರೆ we have to consider the rate of the forward reaction as well as the rate of the backward reaction. In fact, dx by dt, that is the net rate of the reaction, is actually the rate of the forward reaction minus the rate of the backward reaction. Okay, so 100 molecules represent rate of the forward reaction, but out of that 40 molecules has reacted back, which is nothing but the rate of the backward reaction. So the overall concentration of the product B is only 100 minus 40, that is 60 molecules, which represents the net rate of formation of B. So the overall rate or the net rate of a reversible reaction is rate of forward reaction minus rate of backward reaction. So let us substitute equation 1 and 2 here. So therefore dx by dt, that is net rate, is equal to k1 into A minus x minus K2 into X. This is the net rate of the reaction at time t. This is the expression for the net rate of the reaction at time t. Now let us try to understand the situation. Okay, let us imagine this reaction. At the beginning you had highest concentration of B and you had the lowest concentration, highest concentration of reactant A and the lowest concentration of product B. In fact, concentration of product is 0. So what would you expect? The rate of the forward reaction should be very large at the beginning compared to rate of the backward reaction. ಯಾಕಂದ್ರೆ ನಾನು ಆಲ್ರೆಡಿ ಹೇಳಿದ್ದೇನೆ, rate of the reaction is directly proportional to concentration of the reactant. So at the beginning of the reaction, concentration of the reactant is large and therefore rate of the forward reaction should be very high. On the other hand, concentration of the product is very less, therefore rate of the backward reaction will be very less. So at the beginning, the rate of the forward reaction is very large, rate of the backward reaction is very small. But with the time, okay, with the time, concentration of the reactant decreases, concentration of the product increases. So what should happen to the rate of forward reaction? Rate of the forward reaction decreases from its maximum value, whereas the rate of the backward reaction increases from its minimum value, and at a certain instant, okay, at a certain time t, rate of the forward reaction will be exactly equal to rate of the backward reaction, and this situation is nothing but called as the state of chemical equilibrium. So what do you mean by a chemical equilibrium? So it is a state where the rate of the forward reaction will be equal to rate of the backward reaction, or the net rate of the reaction will be equal to 0. So reaction is still taking place both in forward direction as well as the backward direction, but the overall effect is 0 because rate of forward reaction is exactly equal to rate of the backward reaction. So at a certain instant of time, this reaction also reaches equilibrium. And what happens at equilibrium? At equilibrium, the net rate of the reaction becomes equal to 0. So let us try to substitute that condition here. So at equilibrium condition, okay, so the fate of any reversible reaction is it finally reaches the state of this equilibrium. So at equilibrium, the net rate of the reaction becomes equal to 0, or you can also write it as rate of forward reaction will be equal to rate of backward reaction. Okay, and suppose at equilibrium the concentration of the product that is formed is Xe, where E represents equilibrium. So Xe represents the concentration of the product that is formed when the equilibrium state is attained. Or what would be the concentration of the reactant? A minus X will be equal to A minus Xe. So these are the equilibrium concentrations. Equilibrium concentration. This is the concentration of the product B at equilibrium. This is the concentration of A at equilibrium. So concentration of product B at equilibrium is Xe. Concentration of A at equilibrium is A minus Xe. So these two represents the equilibrium concentrations of reactant and product. So let us substitute these condition in equation 3. Therefore, rate of the reaction is now A1 into A minus Xe. Okay, because now I am writing this equation for equilibrium, so I have to substitute the equilibrium concentration. So K1 into A minus Xe minus K2 into Xe is equal to 0. Therefore, K1 into A minus Xe is equal to K2 into Xe. Therefore, K2 is equal to K1 into A minus Xe divided by Xe. Okay, so by using this condition of equilibrium, we have established a mathematical relation between rate constants K1 and K2, that is rate constants of forward and backward reaction. So let us now try to simplify this equation 3 by substituting this relation in equation 4. So we are now trying to express the rate of the reaction in terms of concentration X as well as concentration Xe. What is the difference between X and Xe? X is the concentration of the product at a time t. Xe is the concentration of the product at equilibrium. So let us substitute equation 4 in equation 3 and try to obtain an expression for rate in terms of the concentration X as well as Xe. Okay. So substituting equation 4 in 3, okay, we get the net rate of the reaction at a time t dx by dt is equal to k1 into a minus x minus what is k2 according to equation 4, we will write it, it is k1 into a minus xe divided by xe. This is nothing but k2 into x, k2 into x. Okay, let us try to simplify this equation, okay, by taking a common denominator. Okay, dx by dt is equal to, if I take xe as the common denominator, so this equation becomes k1 into a minus x into xe minus k1 into a minus xe into x. Okay, let us try to simplify the numerator. Dx by dt is equal to k1 into a into xe, okay, minus second term k1 into x into xe minus first term k1 into a into x minus into minus plus k1 into xe into x divided by xe. Okay, so if you see here, the second term and the fourth term, when added, they become 0 because you have minus k1 into xe plus k1 into xe into x. So when you add them, they become 0, and therefore you can write dx by dt is equal to, okay, I have xe and k1 as, sorry, k1 into a as common in the first and third term. So I can write it as k1 into a into xe minus x divided by xe. Okay, so this equation, okay, is expresses the rate of the reaction in the differential form. Dx by dt is equal to k1 into a into xe minus x divided by xe. And I already told you in my earlier lectures that it is sometimes beneficial, okay, or easier for us to express and try to interpret the rate equations in the integrated form. So this equation, okay, say for example, I will call this as equation number 5. Okay, equation number 5 we will try to express in the integrated form. Okay, for before this equation is converted into the integrated form, we have to rearrange this equation in such a way that similar terms are on one side of the equation. So you have x here and here you have dx, so such type of terms should be arranged on one side of the equation and the remaining terms, okay, should be arranged on the other side of this equation. Okay, so let us rearrange this equation. Okay, let us try to rearrange equation 5. Okay, rearranging equation 5 we get, okay, I will take this term to LHS. Dx divided by xe minus x is equal to k1 is a constant, a is a constant, divided by xe is a constant into dt. So we have separated the variables. Okay, the variable x are on one side of the equation, the time is the other variable, it is on the other side of this equation, rest of the things are constants. Now let us integrate this equation. Okay, so on integration, integration of dx divided by xe minus x is equal to, k1 is a constant, a is a constant, xe is also a constant because xe represents the concentration of the product formed only at equilibrium, so it is also a fixed number. So I can remove k1 into a by xe from this integration and therefore I get integration of dt. Okay, so if I integrate this equation, it becomes minus, okay, ln xe minus x. This is the integration of LHS is equal to k1 into a divided by xe into integration of dt, that is t, plus an integration constant I. Okay, let us number this as equation 6. So in order to find out what is the final form of this equation 6, we have to actually find out what is the value of integration constant I. And how do you find out the value of integration constant I? Okay, it is by setting the initial condition, that is at t is equal to 0, the concentration of the product is 0, that is x is equal to 0. Concentration of the product formed from the reaction is 0, so x is equal to 0. So let us substitute this condition, that at t is equal to 0, x is equal to 0. What happens, let us see. Okay, so at t is equal to 0, x is equal to 0. If I substitute this condition in equation 6, so equation 6 now becomes minus ln xe minus 0 is equal to k1 into a divided by xe into 0 plus I. So this term is 0, therefore we get I is equal to minus ln xe. So the value of integration constant is minus ln xe. Now let us substitute equation 7 in equation 6. Equation 7 in equation 6. What do we get? Minus ln of xe minus x is equal to k1 into a divided by xe into t plus integration constant I is minus ln xe. Okay, I is minus ln xe. Now let us shift this term minus ln xe, let us move this term to RHS. So what happens in that case? So if I move this term to RHS, we get ln xe minus ln xe minus x is equal to k1 into a divided by xe into t. If I apply the rule of logarithm, log a minus log b is log of a by b, we get ln of xe divided by xe minus x is equal to k1 into a divided by xe into t. Okay, therefore let us rearrange and find out what is k1. Okay, what is k1? K1 is nothing but xe divided by a into t, xe divided by into t into ln of xe divided by xe minus x. So this is the expression for the rate constant of the forward reaction. Okay, where xe is the equilibrium concentration of the product formed, a is the initial concentration of the reactant, t is time, and x is the concentration of the product at some time t. This is the expression for rate constant k1. Now let us try to find out, okay, what is k1 plus k2. Okay, we need not find out what is k2 now. Let us directly find out, okay, what is, okay, or let us find out what is k2. Okay, okay, you know what is the relation between k1 and k2. What is the relation between k1 and k2? So if I substitute equation 8 for k1 here, I can find out what is k2. So let us substitute equation 8 in equation 4. Okay, substitute equation 8 in equation 4, we get k2 is equal to k1. K1 is xe divided by at into ln xe divided by xe minus x into a minus xe into a minus xe divided by Xe divided by Xe. Okay, so Xe gets cancelled. You get K2 is equal to A minus Xe divided by At into ln of Xe divided by Xe minus X. So this is the expression for K2. Okay, if you compare equation 8 and 9, okay, the only difference in these two equation is here you have Xe in the numerator, you have A minus Xe in the denominator. So this is the equilibrium concentration of product form. This is the equilibrium concentration of the reactant at that equilibrium state. So rest of the terms are one and the same. So the more interesting uh, calculation is what is K1 plus K2, that is the overall rate constant of the reaction, K1 plus K2. So let us try to find out what is K1 plus K2, that is the overall rate constant. So what is overall rate constant? K1 plus K2, that is nothing but equal to, what is K1? Okay, let me write, it is K1 plus, what is K2 according to equation 4? Okay, according to equation 4, K2 is K1 into A minus Xe divided by Xe. This is obtained from equation 4. K2 is nothing but this expression according to equation 4. Let us try to simplify this. You have K1 is a common term, so it becomes 1 plus A minus Xe divided by Xe, which is, okay, if we simplify this, it is K1 into, let us take common denominator Xe. So now the numerator works out to be Xe plus A minus Xe. Therefore, K1 plus K2 is equal to K1 into Xe gets cancelled into A divided by Xe. That is, what is K1 according to equation 8? Let us substitute. It is Xe divided by At into ln of Xe divided by Xe minus X. This is K1 into A divided by Xe into A divided by Xe. So if we cancel, okay, Xe gets cancelled out, A also gets cancelled out, we get K1 plus K2 is equal to 1 over T into ln of Xe divided by Xe minus X. K1 plus K2 is equal to 1 by T into ln of Xe divided by Xe minus X. Okay, so this is the expression for the overall rate constant K1 plus K2 of a reversible reaction. And remember, both the forward as well as the backward reactions are of first order. Okay, so let me rewrite this equation in terms of logarithm to base 10. What do we get if we express this equation 10 in logarithm to base 10? Okay, you can write equation 10 as K1 plus K2 is equal to, let us convert this logarithm, natural logarithm, to logarithm to base 10, multiplying by the factor 2.303. So this equation becomes 2.303 divided by T into log of Xe divided by Xe minus X. So this is the expression for the overall rate constant K1 plus K2 of a reversible reaction where both forward as well as backward reactions follow first order kinetics. Okay, and interestingly, if you compare this equation with the expression for rate constant of a first order reaction taking place only in forward direction, okay, what is the expression for rate constant of a first order reaction? Rate constant of a first order reaction is 2.303 divided by T into log of A by A minus X. So this is the rate constant of a first order reaction taking place only in one direction, that is forward direction, whereas equation 11 is the overall rate constant for a reversible reaction where both the forward as well as backward reactions are of first order. Okay, so interestingly, if you compare equation 11 with this equation, both are very much similar. They are not same, but they are similar. Okay, both contain 2.303 divided by t into log of, here you have a by a minus x, you have xe divided by xe minus x. So here I have initial concentration of a, here I have equilibrium concentration xe. So both equations are very much similar, if not same, they are very much similar. Why? Because both are dealing with a first order kinetics. This is a first order expression for a forward reaction, this is a expression for a reaction which is first order in both forward as well as backward reaction. So this is about the kinetics of a simple reversible reaction where a first order forward reaction is opposed by a first order backward reaction, and where we have assumed that the initial concentration of the product is 0. In the next class we will consider the second case. Again we will consider the same reaction, A giving product B, where both forward and backward reactions are of first order, but now the initial concentration of the product B is not equal to 0. And let us try to find out what is the overall rate constant K1 and K2 and try to compare with this expression.